Hi there, my name is Alex Komodo and I'm from the Applied Artificial Intelligence Institute at Deakin University. Thanks for joining me today for my talk at ESEC FSE 2020. Today, I'm excited to share an architecture tactic that we developed to help software developers integrate their applications with AI-first components, specifically intelligent web services. Let's start off with a recap of what an intelligent service actually is. If we picture machine learning as a tool to build software, we see that there is an emerging trend of techniques that developers can adopt. The left-hand side of this spectrum is the most technical approach, where a developer would set up a training infrastructure and write their own algorithms to build an AI-first application. Without prior expertise and lots of studying up on how to do this, it can be quite confusing for your everyday developer. An abstraction on top of this would be to use an ML framework, like TensorFlow, to plug in a pre-trained model. However, this still requires understanding of machine learning lingo and principles, and both of these approaches need some form of data processing pipeline. A completely different approach is to use a cloud-based service that provides the power of machine learning through RESTful API endpoints. Most developers are already familiar with cloud-based endpoints, and they only need some slight vocabulary to integrate powerful ML capabilities into their apps. So, through the use of cloud-based endpoints that developers are already used to, such services have now been dubbed as developer-friendly machine learning. Now, while this is the vendor's plan, we've been exploring these services for a while and have started to identify some interesting patterns. Firstly, there's been an explosion in these types of services, especially for computer vision. If we look at the marketed promise to developers from some of the bigger players, we can see that they can tap into human-level intelligence using these services. So let's look at a few examples from the documentation and FAQs. They can build custom AI applications without a PhD, or they don't have to build, maintain, or upgrade deep learning pipelines. From our paper at ICSE this year, we identified increasing developer discussion about these services on Stack Overflow. However, many of these developers' issues face substantial pitfalls in computer vision. In short, the state of the art of computer vision is good but not perfect. A study last year showed that a change in 1 pixel in a 32 by 32 pixel image can completely fail image classification. They are also easy to fool through the use of adversarial examples. A good concrete example of this was at Usenix 2018, where facial recognition identified Angelina Jolie from a photo of Jack Nicholson by changing a few pixels in the source image. When we look at the services themselves, they too are not immune. A 2017 study found that Google Cloud Vision can also mislabel images through added noise to the image. Our analysis has helped us identify 9 evolutionary patterns in these computer vision services. They generally fall under 2 broad groups. Firstly, confidence intervals are non-static and evolve with time. Developers write code to assume that these intervals are static. Secondly, changes to the label sets returned from the same image can change with time. To make this a bit more concrete, here are a few examples from a real-world service. So here we show an image that was sent to a very popular computer vision service in November 2018 versus March 2019. The best label in November was window at about 56% confidence. In March, however, this label changed to water transportation, and the service substantially is more confident in this label by an increase of about 43%. So, in less than 6 months, an enormous jump in confidence for a new label despite the same image. Or similarly, the service can become substantially less confident. So, in March it was about 92% confident that this image was black and white, while in November that confidence dropped to 61% to a new label of still life. Or sometimes there are no changes in confidence at all, but the label might be swapped out for another. Here we see that street sign was replaced for signage at a confidence of 89%. So while some services may present minor changes to labels' confidences, Other labels had significant changes that were beyond basic decision boundaries. Next up, cardinality changes occur when the service either introduces or drops a label for the same image at two different generations. Here we see that this image of a milkshake had 10 labels in March 2019, but in November 2018, the only label that was identified was pink. So a further 9 new labels were introduced within a 5-month period. Or fewer labels suddenly become identified. For example, in March, the service no longer associated this image with the terms shrubland, meadow, leaf, lawn, yard, or flora, which it did in November. Alternatively, the cardinality of labels returned may remain stagnant, although as we've shown, this isn't guaranteed. Lastly, ontologies of these labels are non-static, and a label may generalize. So for example, we found that this image of a bus became land vehicle. Or the ontology could specialize, so reptile became iguana. Or lastly, the emphasis of the image analysis may change entirely. So, for example, in this case, it was looking at the background of the image, tree, and now that's switched to the foreground of the image, clothing. So ultimately, these changing results can cause an expectation mismatch by developers as to what labels currently returned by the service will remain the same. Furthermore, we find that these services aren't versioned. A strategy we typically use in software engineering, upon substantial changes to a system, is to version it. But with these intelligent web services, you can't currently request a specific date of the model or its version that you may have tested your application against. This means that developers need to consider how unversion evolutionary changes from an intelligent web service may impact their services in production. It's also difficult to calibrate your domain-specific application with a one-size-fits-all service. All you can request from these services is the image you want to analyze, and sometimes the maximum number of labels that you desire. Developers typically deal with this return score or confidence value using a threshold. These thresholds determine decision boundaries to see whether or not to take action from the service. Determining these boundaries becomes challenging without proper understanding of the underlying service's model. Threshold selection is fundamentally dependent on training data of the service and other factors, such as algorithmic performance, financial cost, and impact of false positives and false negatives. How everyday developers calibrate these values to the service is still a challenge. And to top it all off, all this non-deterministic behavior is always returned as a 200 HTTP success, when really any unexpected behavior from the service should be presented as an error code so that can be plugged in to a deterministic component to deal with error handling. To make this a bit more concrete, consider the motivating example from within our paper. A developer has been tasked by a local nursing home to help them detect falls from CCTV cameras. The developer has limited experience with computer vision techniques, and so opts to use a computer vision intelligence service instead. The developer thoroughly tests the system with a large benchmark dataset provided to them from the nursing home and deploys this system out. However, 3 months later, and the system comes back with lots of false positives. The nursing home complains that the system isn't working as expected. Digging into these issues, the developer sees that the confidence thresholds that were used weren't calibrated correctly, and a lot of labels are now being mislabeled. For example, a person is now labeled as a child. The developer wasn't informed that this evolution was occurring, as it was never documented by its service providers. And now the developer isn't sure how to deal with unexpected behavior in the future. So how can the developer ensure that the service will behave normally moving forward? To build a robust solution, our developer has come up with 4 requirements to improve their software and make it more robust. Firstly, they want to define a set of error conditions that specify the types of evolution that can occur for the intelligent service. Secondly, they need to ensure that the software has an inbuilt notification mechanism informing them of behavioral changes in the cloud service. Thirdly, they need to monitor the evolution of intelligent services for changes that affect the application's behavior. And lastly, they want to implement a flexible architecture that is adaptable to different intelligence services and to permit reuse different application contexts. Unfortunately, the current architectural approach doesn't meet any of these requirements. The current approach presumes that Intelligent Cloud Services Client SDK is directly embedded within the client app. This direct approach risks evolutionary changes from the cloud service leaking into the client application, thereby leading to less robust apps, as we're seeing. Instead, we propose 4 key workflows and a new architectural tactic to assist developers like the one in our example to deal with evolutionary behavior. Our proposed approach is to use an intermediary that sits between the client app and the cloud service, in this case, a proxy server. Developers initialize this proxy server with 3 key inputs. Firstly, a benchmark dataset specific to the client application's domain is uploaded to the proxy server. The dataset is used in conjunction with the second input, a schedule, which is stored on the scheduler component used to trigger checks against the cloud service using the benchmark dataset to detect evolution. Thirdly, tolerated evolution behavior and confidence threshold are tuned via the confidence threshold tuner. Once this is done, the first workflow of the proxy server is to obtain a baseline behavior by sending the benchmark dataset through to the client SDK, which is also living on the proxy server. The benchmark dataset is sent via the client SDK so that all images are analyzed and the current behavior of the service is captured. The resulting behavior is encoded within a behavior token, which encodes tolerated rules specific to evolutionary behavior. The behavior token is sent back to the client application where it is stored for future use. Now, to make future requests to the service, requests must be made to a guarded facade API on the proxy server. Before that request is forwarded to the intelligence service, the behavior token from the client is validated with the behavior token on the proxy server to ensure that no substantial evolution has occurred according to its encoded rules. If the rules aren't violated, then the request is forwarded. Eventually, the scheduler will trigger. This causes the benchmark dataset to be sent back to the cloud service. This also produces a new behavior token. When we try to submit another request with a stale behavior token on the client's behavior token is now compared against the proxy's behavior token. If any of the tolerated rules are violated between the old and new behavior tokens, then the proxy server does not forward the request. The Facade API handles this deterministic error code using a HTTP 412. Exhaustive error handling through HTTP satisfies our first requirement. Different types of evolution are detailed now as error codes instead of being hidden evolution that's undocumented. The threshold tuner component helps us fulfill our second and third requirements. An implementation of this tuner is detailed in our complimentary demo track paper, so please give this paper a read or watch our associated videos for more information. The benchmark dataset, behavior token, service client SDK, and scheduler also help satisfy requirements 2 through 4. More details about this are included within our paper. We implemented an approach of this intermediary over a 5-month period from November 2018 to March 2019. This technical evaluation of our implemented approach identified 331 cases of evolution on a popular computer vision service. To explore these evolutionary changes, we looked at 5 broad categories of images and explored both the confidence changes and the changes in the ontology. In our paper, we give 3 concrete example responses with and without the proxy server. We can see that errors clearly indicate evolutionary behavior which exceeded our encoded thresholds. In the first case, confidence changes within an image was sent to the service in November versus March, and this increased by, on average, 11%, which has substantially exceeded our threshold of plus minus 1%. Without the proxy approach, the substantial changes in confidence would have simply been returned as a 200 OK, as opposed to the case where the conditions within our behavior token were violated, and therefore returning a 412 precondition failed. In the second case, label cardinality changes were detected beyond our threshold set of ±5, whereby the same image in November had 4 labels missing in March and vice versa. In the third case, we gave an example of ontology specialization, in which label ontologies changed substantially and expected labels were missing. Now to some implications. For cloud vendors, we suggest that they provide some sort of auxiliary service similar to the proxy approach that we used in our paper. This will help developers build more robust applications using their service by decoupling the model from its evolution. We suggest that vendors encourage their developers to calibrate their domain-specific applications to their generalized services through the use of benchmark datasets. Further, we suggest that vendors provide best practice guidelines for dealing with service evolution, or at least make it a bit more prominent that the service does evolve. Lastly, we find that there is a mismatch between evolution of internal models and the APIs themselves. So we suggest that vendors align their releases of model updates to when a new API is released. Now to the developers. First and foremost, monitoring these intelligent web services is a must. Developers must frequently assess each service against a benchmark dataset and calibrate these services' confidence values to decision boundary thresholds appropriate to their app. Now, if cloud vendors do version their APIs, developers also need to check the extent of the model changes in the API update against their current app. Lastly, we suggest that developers leverage the intermediary approach provided in this paper to make their applications more robust, rather than directly hitting the service with the client application. Now, a few implications for project managers. Firstly, the cost of intelligent service evolution must be factored into project pipelines. Tasks need to be scheduled to help maintain the service evolution through a maintenance infrastructure. And similarly, tasks need to be identified to see when the evolution occurs before projects lock down to a specific intelligent service. That about wraps it up. I hope you found the talk interesting, and please feel free to read our paper for more detail, including how the approach can be used beyond computer vision services. Thanks, and we look forward to your feedback.